This is lecture 5, part 1, and we're going to start a new topic called support vector machines. And in the previous two lectures, we talked about neural networks. So the problem with those is that we do not really know a lot of the theoretical properties and statistical properties of neural networks, but they work really well in practice. They are being used to solve lots and lots of different problems. So what we're going to do this time is we're going to do the opposite. We're going to study support vector machines, where we know a lot of the theoretical and mathematical properties of this algorithm, but they don't really work in practice. So what it means is not many people are actually using it, but everyone knows about it. So you should probably know about it as well. So let's get started. So I want to first go back to the perceptron algorithm where things can be separated by a line. And suppose we have two classes, and we have used the example of cats and dogs, dragons and not dragons. So I'm going to change again this time, and maybe say arts and trash cans. So if you don't know the reference, it's from the movie Wonder Woman 1984. And in the trailer, there is this line. Sorry. In any case, let's get back to machine learning. And if we are training a perceptron, for example, then maybe it will end up something like this, because all we are doing is kind of minimizing the number of mistakes. And the mistake here is 0, so it's okay, it will stop here. Or maybe it will say stop like this. That's possible as well. We probably want the line in the middle, but we probably won't get that one. So for example, if we want to actually classify something here, it will be classified as arts, but well, it looks like it's kind of very close to trash cans, so it should be classified as a trash can. So we probably want a line that's kind of better in the sense that it's in the middle, and we want something like this. So now the problem is, how are we going to mathematically define we want the line, or in higher dimension is the plane, a plane in the middle? So someone very clever says we're going to use a very thick line, and if the thick line still classifies everything correctly, then we want the line to be as thick as possible. So we have basically a very thick line. And we're going to call the thickness of the line the margin. And if we have a line with the maximum margin that separates the two classes, then we're going to use that line. We're going to use the line in the middle, basically. So now we are trying to solve the max margin problem. So at the moment they look similar, and it turns out they will use gradient descent again. So let's mathematically find out what we are actually maximizing, how to actually compute the margin, and so on. So this is basically what I just talked about. The SVM, the formula is exactly the same. We're using a line, and whether it's above 0 to classify whether it is class 1 or class 2, and we're going to maximize the thickness, or the margin of the thick line. And one thing I didn't mention is that the instance, or the points that hits the thick line, they are called support vectors. That's why the algorithm is called support vector machines. So for example so I guess this one and this one, they are support vectors, and these three, they all look like support vectors. So basically the thickest line must hit at least 2 of the points. So those points are called support vectors. And here is a preview of what we're going to do. We're going to minimize the square norm. And the reason is that this is related to the margin. And we're going to use gradient descent, and the problem will be there will be no gradient because this thing is not differentiable. So we're going to extend it to something called subgradient. And the process you will see is actually similar to the perceptron algorithm. So let's start with the mathematics. First, we need to find the margin. And I'm going to use a diagram instead of just going through the math. Let me draw maybe a wider line. And let's say the axes are, say, here. So here we have 3 lines, basically. You can view this as a very thick line, or you can view this as we have our W transpose X plus B equal to 0 is the one in the middle, and the one that we are going to use to classify stuff. And we have a line above it, say maybe 1 unit above, and let's call that the plus line or the plus plane in higher dimensions. And W transpose B equals to -1. It can go down by -1. So geometrically, we are making some assumptions. So for example, here it will be one of the weights is 1. So maybe say assume W2 is 1 or something. But if you have W2 not equal to 1, you need to scale these two numbers, but we're not going to do it here. We're going to just say one of them is 1 unit above and the other one is 1 unit below. So again, this one is called the plus line or the plus plane, and this one is called the minus line. This is -1. Okay. So now we're going to figure out the margin. So the first and most important thing is the margin is not 2, because the margin is this distance. It's not like this distance. So we actually need to figure this out. And the problem is it's hard to find it directly. So maybe let's assume it's some number. So one thing remember from the first lecture, we talked about the weights are perpendicular to the line. So in particular, we would have maybe like the W vector is something like this, and it's pointing towards the direction where the class is 1. So let's say this is class 1 and the other side is class 0. And this is class 1, this is class 0. And this vector would be some kind of fraction of the weight. So let's call it lambda. So lambda W, then that would be minus lambda W. But we know this point is on this line, and we know this point is on the plus line, and this point is on the minus line. So we do have a lot of equations. Maybe we should write all of them down. And let's try that. So suppose we have a point. Let that point be x, say xi, one particular point. Then this would be xi plus lambda w, and this would be xi minus lambda w. And we can substitute these numbers, these vectors, back into the expressions. And the first one will be W transpose xi plus lambda w plus b is equal to 1. And we're going to skip the middle one, and we will have the last one being -1. So you have two expressions. It looks like they need to be taken the difference of. And let's do that. So a lot of stuff will cancel out, like this part and this part. So you only have this multiplied by this minus this multiplied by this. So it's 2 times lambda W transpose W is equals to 2. Okay, so now we can solve W. W is 1 over, lambda. We can solve lambda, and lambda is 1 over W transpose W. So if we know lambda, then we can know the margin, right? So margin is just the length of, like, double this lambda W vector. So in particular, it's 2 times lambda times the length of W. So I'm using the norm notation. This is just the length of W, which is square root of W transpose W. Right? It's the sum of, say, W1 squared plus W2 squared, which is just W transpose W, and you square root it to get the length. And let's actually substitute this lambda in. So it's 2 over W transpose W multiplied by square root W transpose W, and one of them cancels out. So it just becomes this. Sorry. This. So great. Now we have an expression for the margin. And we can set up the optimization problem now. So all the class 1 points should be above this, and all the class 0 points should be below this. And also we want to maximize this margin. This is our problem. And indeed, it's this. So let me repeat this. When class is 0, we want it to be below the minus line or the minus plane. And when the class is 1, we want it above the plus plane. And we want to minimize the margin. So this seems like redundant to have 2 constraints. So we're going to combine it into 1. So one trick that we used in the quiz, in the perceptron lecture, is expressing -1 and 1 as 2 times either 0 or 1 minus 1. So say if yi is 0, then this is -1. If yi is 1, then this is 1. And then you can combine these 2 inequalities into 1. So now we have this, and we want to simplify this thing because this doesn't look like easily differentiable with respect to W. So one good property is if you want to maximize 1 over something, and that something is positive, it's equivalent. Note that they are not the same, but they are equivalent. They will find the same W if you just minimize the thing in the denominator. So here we are maximizing something like 1 over x, and here we're just minimizing x. They are basically equivalent. And there is actually one extra step because we don't have the square root now. So if we maximize square root of something, and if we maximize just that something, they are the same because the square root is an increasing function. So again, it does not matter. So the wy, I just get rid of the square root. And also, if you multiply something by a constant, it doesn't matter as well because you'll find the same w. Again, they are equivalent, but they are not the same. You will not get the same number if you maximize this and if you minimize this, but you will get the same w. So let me say the same w. So that's all we can do here. And if we want to do gradient descent, maybe we should substitute this thing in here, but it seems it's very difficult to do at the moment. So we do need something else. So in the process of doing that something else, so that we can substitute this constraint back into the objective or the cost function, we are going to relax the constraint that every single point needs to be classified correctly. We will allow some mistakes. So we will combine those steps, and we will call the resulting algorithm the soft margin SVM. So in particular here, we are calling this the hard margin SVM, where everything needs to be classified correctly, and we're not allowing any mistakes like in the perceptron algorithm. So in the next part of the lecture, we will relax it, and we will be able to substitute this W back into the objective so that we can get the gradient descent step.